In this talk, I explained that impedance spectroscopy of halide perovskite solar cells captures the hysteresis effects. Hysteresis means that the go and return pathway in the current voltage curve is different. So there is some important memory effect, and it can be related to different causes, like the formation of interfacial layers in the perovskite solar cell. It can have different shapes because the forward scan can be smaller than the return scan, or this is normal hysteresis, or in the other way around. Hysteresis has been decreased in high-performance solar cells, but it's still present in many cases, like this tandem solar cell. And one technique to measure the cells is to measure the equivalent circuit by impedance spectroscopy, so both things are connected. So we would like to learn the amount of hysteresis, not just measuring directly the curve, but from another predictive method that can give you parameters. And this is the role of the impedance spectra. And then if we can connect both things, it will give us insight about the causes of hysteresis, and we can use it in other devices like Memristors, where hysteresis is a good property because it's a switching device and the memory effect is positive. We have recently published a review of the impedance spectroscopy of halide perovskites. Is this paper with Antonio Guerrero and Germán García Belmonte. In general, in the solar cell, you are interested in the JV curve, which will give you the power that you can extract and the efficiency. This is steady state, but then you can go to a point of steady state and make angular perturbation of current versus voltage. And the relation gives you a impedance spectroscopy at each frequency. So the arc, for example, characterizes the resistance, but now you also measure the time delay via capacitance and inductor. What you do in practice is to scan different points of voltage, and then there will be very strong transformation of the spectra because the solar cell is very different than a short circuit or open circuit or close to the maximum power points. And this is the method to track these properties. And then we use an equivalent circuit to condense all this information. The elements will be changing with voltage because the spectra change, but the intrinsic model is unique. And then we have also the characteristic times that are related to the time transient, the case. In the halide perovskite, we have a lot of complexity because electronic transport in the diode structure is coupled with ion transport. The ions can go to the surface and create polarization. So that we have the capacitance versus frequency has two main components, has a high frequency component, which is the electric relaxation by dipole oscillation, and a low frequency large capacitance that is associated to the ionic double layer. So then we have made these measurements, and many other people. So there is a consensus that the starting point is this spectra with two features, high and low frequency, well described by this equivalent circuit. And then it will be the elements changing with the voltage exponentially. This is very important because whenever you make a perturbation, you will have a strong change of the internal characteristic. That's what makes the relating the hysteresis and impedance a difficult and interesting problem. We talked about the resistance and capacitance in the elementary equivalent circuit, but perovskite have also inductive components, and this has been recently described generally as a chemical inductor in JACs by me and Antonio Guerrero. So the inductor is an impedance where the is proportional to the inductance and the frequency, and it has characteristic decays in which the voltage is depending on the derivative of the current. So typically we have the inductive coil of electromagnetic induction discovered by Faraday that we can represent, for example, with magnetic materials, and they give us an inductance in the equivalent circuit. But there is another phenomenon which we have called the chemical inductor, which doesn't have any coil. It's another operation, usually by coupled chemical steps, and we call this the chemical inductor. The first model for the chemical inductor is a neuron model, the Fishhorn-Nagumo model, and it contains two equations, simple differential equations, but they are highly nonlinear, and they are combined and they give the oscillations of a neuron. And the Memristor also has this same structure. The Memristor has a conductance equation in which the current related to voltage, but the conductance functions has a slow variable x, and the x has a separate dynamics. So to the Memristor equation, here I add the capacitive charging that is always at the interface or by the bulk capacitance. And then we have this structure with a variable x that has a separate equation. And this is the model for the chemical inductor, whatever the interpretation. Here is current voltage, but X can be many different mechanisms in chemical reaction, in recombination, in corrosion, etc. If I linearize the previous equations, then I have a linear model and I can calculate impedance spectroscopy. And we obtain that by this additional differential equation for the slope variable, we have RL, which is the chemical inductor. So this general dynamic structure will provide a chemical inductor. So in summary, we have a fast slow system because the system has two different relaxation times. We have a fast variable influenced by a slow current, and the slow current is delayed, how it adapts to the external voltage. And that will generate the chemical inductor, and the impedance will have an RC from the fast variable, but when the inductor becomes large, it will show also an impedance in the fourth quadrant, which is related to the negative capacitance, but there is no negative capacitance here. It's a positive chemical inductor. I just want to mention that this model we have used like 15 years ago for describing many types of solar cells showing negative capacitance. Is the same model with the RL element here, published in Nanoletters. In organic LEDs, it was found in different types of solar cells, and it has been found in the perovskite solar cells many, many times, like in this crystalline solar cell. The model comes from neuron theory, and you can find it in neuron models like the Fishhorn-Nagumo model. And the first measurement, to my knowledge, was done by Kenneth Cole in 1940 in the measurement of the giant axon squid that gave rise to the biological model from the neuron action potential. Now we go to the topic of hysteresis in halide perovskites. And what happens is that we have to measure the current voltage curve. So we change the voltage with time, make a voltage ramp, but in reality it's made of small steps. So if these steps are slow, at the end of each step, you can be in equilibrium. So it doesn't matter forward or backward scan. But if you make the steps faster, there is an internal relaxation time governed by the equivalent circuit, so that the system will not go to equilibrium at each time, and there will be a difference. And this is what we mention hysteresis. So here the forward voltage JV curve is smaller than the reverse, and this is because RC hysteresis or capacitive hysteresis. This is because in capacitive hysteresis, the forward current is proportional to the capacitance and scan rate. So at higher scan rate, you have more current. So you add a current so that the forward current is larger in absolute value than the steady state current. And this was related in 2015 already, correlating the hysteresis with the interfacial capacitance of the perovskite solar cell. But then it was found another behavior in which instead of the forward being below the reverse in the photocurrent, it's the other way around, and this is called inverted hysteresis, where the hysteresis index becomes negative. And we have these two cases, as I said before, and we want to distinguish them. So in addition to the capacitive hysteresis explained before, we have also the hysteresis caused by induction. And induction is like a negative capacitance, so that instead of increasing the current is decreasing. So it goes the other way around. So we have the inverted hysteresis related to the dominance of inductive elements in the equivalent circuit. This understanding is going to give us a very good control over hysteresis properties, because we can measure the impedance and see, for example, in this case, a transition from capacitive with the two arcs at low voltage to inductive at high voltage. And then at high voltage, we expect inductive feature, and at low voltage, we expect capacitive hysteresis. And this is exactly what happens. So that now we can quantify the hysteresis not just by measuring it, but we can first make an impedance measurement, and the structure of the equivalent circuit will tell us what is going to happen with the hysteresis. And we have presented many different analyses, and they are basically coherent, the direction of hysteresis with the dominant elements of the equivalent circuit at low frequency. So in summary, in capacitive current, the transient current increases, so that when we have a capacitive equivalent circuit, we will have regular hysteresis. The forward current is smaller than the reverse current when we plot the JV curve. Inductive current goes the other way around. Approximately, the forward is more negative than the positive, so that it creates inverted hysteresis, so that the regular hysteresis is capacitive, happening in the low voltage domain of solar cells, and the inverted hysteresis is found many times in Memristors. We can do more, as we show in this work, and correlate the equivalent circuit elements at different voltages to the amount of hysteresis. But this requires an integration, because we are scanning in the JV curve over many different values, varying exponentially of the equivalent circuit, so you need an integration procedure. Now we will describe the perovskite memristor in time and frequency domain. The memristor is a state that when you cycle the current voltage, it has a big difference between a basic high resistance state and an activated low resistance state. So this is a switching device, and this is the basis for memory applications and also for making synapses in artificial neurons. And this is actually the behavior of a halide perovskite memristor, showing the transition that is on set at certain voltage. And you can see it's a big inverted hysteresis. So this is a good opportunity to study intense hysteresis effects in the halide perovskite family. So it was found that when the device is in the high resistance state before the transition, we have simply the double arc structure, and then when you go close to the transition to the low resistance state, is appearing the inductive element. And this was done by Antonio Guerrero and Cedric Gonzalez. Now we can make a model of the type of the chemical inductor. And this is one example of this model with the fast and the slow modes, which is a function that will rise at a certain voltage and saturate. And from the model, we can calculate also the impedance spectroscopy response. So we can correlate the hysteresis and impedance properties, obtaining, of course, due to this structure, the negative, the inductive feature of the chemical inductor. So now there are many possibilities. One has to measure, and indeed we have measured Memristors. And then we find something very interesting, which is the big hysteresis properties. The onset voltage depends on the scan rate, and the impedance makes a transition from capacitive and low voltage to inductive. But it gets much features. It's not only this is the chemical inductor at 0.4 volts, but here there are more features. We need a more complex model, and this model is obtained with 3 combined equations, which is the total current equation, a diffusion current, and a reaction variable. So there are 2 variables, ICF, and using this 3-dimensional model, we can describe accurately the impedance spectroscopy and the JV curves different scan rates. So that this seems to be very successful because there are very few models for Memristors, and this is also an extraordinary result for the analysis of perovskite solar cells, because in modeling the perovskite solar cells, you require very complex drift diffusion simulation with ions, with dozens of parameters, and here you can build a model making very few equations, 2 or 3, and obtain a lot of information about the dynamical characteristics of the behavior of the perovskite device. For example, we can describe with this 3-dimensional model this crossing of the JV curves, in which there is the transformation of capacitive to inductive hysteresis that I mentioned before, but there is a very nice crossing at the different scan rates. And this we can describe very well with the model. Here is capacitive, here is inductive, and we obtain a quantitative description of these features. And we can do more. We can use the 2-dimensional model again and make the transient response. And this transient has charging and discharging due to capacitors and inductors. And then we can generate the time domain response just with 2 equations, where the coefficients are functions of the voltage. So this is not totally trivial to go from one thing to the other, and this method is in progress, and I hope that we can obtain a general method where we can have the voltage dependence of the elements and see how it's going to behave in the time domain. So in conclusion, we have now a basic understanding of a correlation between JV curves and even time transients and capacitance response, because we have regular hysteresis is capacitive due to the surface capacitance of the halide perovskite, and inverted hysteresis is inductive due to the chemical inductor effect of the halide perovskite that is probably related to ion control recombination. This is low current is probably a recombination at the surface, and so we can distinguish the 2 circuits and behaviors by measuring the impedance spectroscopy. We have an idea what is going to happen, how much hysteresis there will be, how are going to be the current voltage curves, And then we can state that the equivalent circuit evolution controls the dominant hysteresis. So I want to thank my colleagues Antonio Guerrero, Agustín Bou, and Cedric González. Recommend you to send papers to the Journal of Physical Chemistry Letters, where I am the editor. And this is my book for the people interested in the physics of solar energy conversion. And it has been converted into a series of videos that are freely available at the Energy site, and you can look these videos if you are interested in the basics of solar cells and solar energy conversion. Thank you.